So in this session we are going to see how to design a modulo counter. In the last session we have seen how to design a 4-bit triple counter. So a 4-bit triple counter can be also called as modulo 16 counter because it is able to count 16 clock pulses. So a counter of any number of a counter which can count any number of clock pulses can be designed. So such a counter is called as modulo n counter. So in mod n counter, n refers to the number of clock pulses the counter is able to count, and this number n must be less than or equal to 2 power n, where n refers to the number of flip-flops. So in a modulo n counter, the counter output must be cleared, in the sense the counter should be reset to 0 after the application of the nth clock pulse. So in order for clearing the flip-flops at the nth clock pulse, normally a NAND gate is used, to which the outputs of all the flip-flops that are taking value 1 at the nth clock pulse is applied as the input, so that the NAND gate output becomes 0 at the nth clock pulse, and this NAND gate output is used for clearing all the flip-flops in order to reset the counter to 0. So most popular modulo n counter is the modulo 10 counter, which is used for counting 10 clock pulses, which otherwise also is called as a decade counter, in which the counter will only take 10 clock pulses as the input, therefore it will only produce 10 counts from 0 to 9. At the 10th clock pulse, the counter output momentarily becomes 1010, wherein the outputs Q1 and Q3 are taking the outputs at binary 1, and these binary 1s are used for clearing all the flip-flops. So if we look at the timing diagram of the clock pulse and also the counter outputs, what we see is that the values of Q0 and Q1, Q2 and Q3 are the same until the 9th clock pulse. At the application of the 10th clock pulse, what we see is that the outputs Q1 and Q3 become 1. They should be forced to return back to 0, so that the counter will be reset to 0 after the application of the 10th clock pulse, and then it will start repeating the counting process from the beginning. So this is how the flip-flop is supposed to be designed. So in order to generate the clear signal from Q1 and Q3, all we require is an AND gate in the normal 4-bit triple counter, to which the inputs are taken from Q1 and Q3, which normally are taking the values 1 at the 10th clock pulse. Hence the output of the NAND gate becomes 0 at the 10th clock pulse, and this bit is used for clearing all the flip-flops at the 10th clock pulse. So until the 10th clock pulse, we can see that the outputs Q1 and Q3 together are not taking 1 and 1. So it's only at the 10th clock pulse they are taking binary values 1 and 1, and hence the flip-flops are cleared only at the 10th clock pulse. So this is how modulo 10 counter or decade counter can be designed. So similarly, modulo n counter with any number of n value can be designed. Only thing what we need to see is that at the nth clock pulse, we have to examine the output of a 4-bit triple counter and see which bits are taking value 1, and those bits have to be applied to the NAND gate. It can be a 2 input NAND gate, or it can also be 3 input NAND gate, depending upon the number of bits which are taking value 1, and the output of the NAND gate should be supplied to the clear inputs of the flip-flop, so that at the nth clock pulse all the flip-flops are cleared. So this is the way we design a modulo n counter, and here it is a modulo 10 counter, and hence it's also called as a decade counter. Now let's look at a case where the counting process has to go in the downward direction from the topmost count towards 0, and such a counter is called as the down counter. So far the counters that we have seen are up counters, wherein the initial count is 0, and as the clock pulse is being applied, the counting will go in the upward direction, whereas certain applications required counting process to happen from the topmost count towards 0, and that such a counter is called as the down counter. So for the design of down counter, initially all the flip-flops have to be preset to 1, and hence we use the preset input of the flip-flops for presetting the flip-flops. So the initial count of the flip-flop is made as 1 1 1 1, and then the flip-flop is used for normal counting. And the difference what we see here is for the down counter, the clock input of the succeeding flip-flop is inputted with the complemented output instead of the normal output. So Q0 dash is inputted to clock 1, and Q1 dash is inputted to clock 2, and Q2 dash is inputted to clock 3, as compared to the up counter. And such an application of the clock pulse will enable the counter to count the clock pulses from 1 1 1 1 downwards towards 0 0 0 0. So this is the way we design a down counter. So with that we come to the end of asynchronous counter. So under asynchronous counter, in the previous lecture we have seen how to design a 4-bit ripple counter, and in this session we have seen how to design modulo 10 counter, and also how to design a down counter. So thank you.